Hi, in this video we're looking at the differential of exponential functions. Now, 2020 is going to be the year of the exponential function, isn't it? We're going to look at how we go about deriving these exponential functions. Functions where the exponent is where our variable is situated. And these are the sort of curves that we're going to need to look at and be able to find derivatives for them. Now, in order to do this, I'm going to use a graphing package, and I'm going to deal with a thing called the gradient function, which you may or may not have been introduced to last year, but which I think is really useful in trying to understand what the gradients of these particular curves are going to be. So what I'm going to do is I'm going to go to my graphing package, GeoGebra, and I'm going to start out with a very simple exponential curve. Let's say y is equal to 2 to the power x. And there's the line y is equal to 2 to the power x. We recognize that curve well enough. Now what I'm going to do is I'm going to go and put a point somewhere on that curve. Put it over here. And I'm going to take a tangent to the curve at that point. So I'm going to select the point, select the curve, and there is my tangent. Now that tangent has a slope, and I can work out where that slope is and get the package to tell me what the slope is. And as I move the point A up and down the slope, so you'll see the tangent, the gradient of the tangent changes. And that's what we'd expect, but we just are able to see it changing as we move it along. Now, what I'm going to do is I'm going to find a new function. And that new function I'm going to call the gradient function. And to do that, I'm going to make a second point. I'm going to call this second point over here d for the derivative, because that's what the gradient function is. It's the derivative. And what I'm going to do is I'm going to plot this point, the x-coordinate of this point over here, of the point A. So I'm going to take x of the point A, and with it, I'm going to plot the gradient of the curve at that particular x value. So I'm going to put in the slope, which is m over here. So you can see these two things are lined up perfectly. A has the coordinates 1.38 and 2.6. So when x is 1.38, the y value is 2.6. That's the point A. Point D down over here, well, that's got an x coordinate of 1.38, just like the point A. But this 1.8 is the gradient of the curve at that point A. Now, I'm going to move this point along the curve, and we're going to see that the gradient, that point D, is going to shift as well. Now, it'd be quite useful to see how it's shifting, because it seems to be following a certain sort of pattern. So what I can do is I can go and put a trace on this curve, on that point, and now, as I pull this up and go along the curve, we'll see that I'm getting a new curve as well. I'm getting a curve over here, and I now need to try and figure out what that curve is, what the derivative of that curve is. And in fact, the black curve over here is the line y equals natural log of 2 times 2 to the power x. And there we can see the red line over here. There is the line y is equal to ln 2 times 2 to the power x. Now, that's all good and well. That's what the derivative looks like for y is equal to 2 to the x. But now we didn't want to know about 2 to the x. We wanted to know about y is equal to e to the x. So I'm going to go back to my initial equation over here, and I'm going to amend this slightly, and I'm going to make this, instead of 2, I'm going to make it e to the x. That's all good and well. That changes that. And I'm just going to delete this over here because we don't need that. And if I go and just shift the graph slightly, we lose that trace. Now, it seems like I've got a point over here where the point D, the gradient point, and the point A seem to be on top of one another. So let me run this point down here and we'll see what the gradient function looks like. And I run it down, and this is what you notice. Ooh, hang on. The gradient function for e to the x is itself e to the x. This is kind of weird, but this is one of the key things about the function e to the x and why it is so important. It's so important because the derivative of e to the x is itself e to the x. So if we go back to our original set of questions, we can see over here, if we want to find the derivative of y is equal to e to the x, so in other words dy dx, well, that's simply going to be e to the x. Now, what about other exponential functions? What about functions where I've got 3x or minus x or 2x plus 3? We're going to look at this, and we're going to go back to that graphing package that we had before, and we're going to see what happens when I go and change these particular functions. So if I go back over here and I just amend this one slightly and I make this 3x, and I get rid of that previous tracing, well, we can see now that the curve is going to be a lot steeper, and we seem to have d at a slightly different point. Well, let's see what happens as I move along this curve. Well, I seem to have things crossing through slightly different points over here. I don't know where it's crossing through the y-axis. Let's just go in a little bit further. Let's see what happens. So it looks like as I move along here, I'm just going to animate this point, just so we can get a whole lot of nice points together. We seem to have a new exponential function. It's an exponential function that's not going through 1, it's going through 3. It's 3 times as much. So maybe we're looking at y is equal to 3 times e to the power 3x. And hopefully you can see in the background over here, I'll just change the color of that. Let's make it a nice vivid blue so it stands out. We can see that that is what our derived function is. It's this point over here. Where's my point A? There it is over there. Let's just pull that down a bit. And let's zoom in a bit more so we can see this nicely. So let's get the track on, and we can pull this down. And there we've got the points going through this curve. Y is equal to 3 times e to the x. And so the derivative of y is equal to e to the 3x, so dy dx, that's going to be 3 times e to the 3x. Is that just by chance, or is there something happening there that we should be aware of? Let's go and take a look at what happens when I change this not to 3x. Let's go and change this, e to the minus x. Going to get rid of that graph over there. We don't need that anymore. And now when I go and run my points through the curve over here, I'm getting something else happening. I'm getting something different happening down here. And now we've got to try and figure out what is that curve. Well, when I'd worked with it before, what was in front of the x over here came down to the front. So maybe if I go and put over here y equals minus e raised to the power minus x, maybe I'll get my curve. Yes, you can see it over there, that red line. That is matching it perfectly. So if I go back to my set of examples, what do I have here? I've got dy dx, and that's going to be minus e to the minus x. So we look at the next one. E is equal to 2x plus 3. Right, I had to do a bit of quick editing there because I lost my point D. So here we've got y is equal to 2x plus 3. There's the equation over there. There's the red line. Let's just get rid of this one down here. We don't need that. And let's see what happens as I run my point along here. I'm getting a curve that looks very much like a exponential curve, but something is happening to it. What is the situation that we're going to have here? Well, what we took before was we took the number in front of x before. But now what are we talking about over here? We need to think about this thing over here. And in fact, what we're going to need to do is we need to think about this as being a compound function. So if I go back to my statement over here, and let's just take a look at this algebraically. So if I'm going to say let 2x plus 3 equal a, I can then say that I know dA dx is going to give me 2. So my statement now is no longer, let's just get a bit of space in here. My statement now is no longer y is equal to e to the 2x plus 3. It's y is equal to e to the power a. And I can work out what dy dA is because I've already done that over here. That's going to simply be e to the power a. And so if I want to know what dy dx is, using my chain rule, I can say this is going to be dy dA times my dA dx, and that's simply going to be e to the power a, that's 2x plus 3, and that whole thing needs to be multiplied by dA dx, which is 2. So let's go back to the graph and see whether that will in fact hold. If I go and take that function and input it, so in other words, we're looking at y equals 2 times e to the power 2x plus 3. And we can see there is the curve. It's showing it to be exactly the same. And so we have a situation now. The situation is this: if we deal with exponential functions, we're going to have to deal with this function as a compound function. We go back to the set of examples. We're going to treat this thing over here on the right hand side as a compound function. I've got something happening to the x. It's being multiplied by 2 and being added 3 onto it. And then that is being raised, is what the e is being raised to. And so we have this statement coming up over here. If f of x is equal to e to the power of some function, g of x, then this should be f dash of x, by the way. It should be f dash of x. F dash of x is going to be the derivative of this power multiplied by e to that original power. And that's really coming from the chain rule and our implementation of that. In the next video, I'm going to go through some examples on this. Otherwise, this video is going to be too long. I'll come back to the next video and see how we go with the examples. Goodbye.